Have you ever wondered if life once thrived or still exists on Mars? From ancient oceans and microbial fossils to mysterious methane bursts, Mars has fueled some of the most fascinating theories about extraterrestrial life. What if our neighboring red planet holds the answers to questions about the origin of life itself? Join us as we explore 7 mind-blowing theories about life on Mars that could completely reshape how we see the universe. Martian microbial life in the ancient past. Mars wasn't always the cold and barren desert we see today. Billions of years ago, the planet had an entirely different environment, one that might have been perfect for supporting microbial life. Scientists believe that during its early history, Mars had flowing rivers, lakes, and even large oceans, along with a much thicker atmosphere that could have created stable conditions for life to thrive. One of the most fascinating clues comes from the discovery of ancient riverbeds, deltas, and mineral deposits scattered across the Martian surface. These features point to a time when liquid water was abundant on the planet, and where there's water, there's a possibility for life. On Mars, these wet environments may have been home to microbial colonies. NASA's Curiosity rover even found organic molecules in Martian soil, which could have formed in the presence of ancient life. While they aren't definitive evidence, they make a compelling case for further exploration, especially when you look at extremophiles on Earth, microorganisms that thrive in harsh environments. From boiling hot springs to deep-sea hydrothermal vents, life on Earth has proven incredibly resilient, suggesting that if microbes could survive such extreme conditions here, similar life forms could have adapted to Mars. Early Mars likely had geothermal heat and volcanic activity, providing energy sources that could have fueled life in much the same way. Future missions like Perseverance and ExoMars are designed to dig deeper into this question by studying ancient Martian rocks and drilling into the planet's surface, searching for biosignatures, chemical or structural markers that indicate the presence of past life. If evidence of ancient microbes is ever found, it would reshape how we understand the origins of life, not just on Mars but across the universe. Mars might not just be a neighbor in space, it could be a key to answering one of humanity's oldest questions: are we alone? Methane mysteries and living organisms. Mars has been keeping us on the edge of our seats with its methane mystery. For years, scientists have detected fluctuating levels of methane gas in the Martian atmosphere, raising the question of its origin, especially since on Earth, methane is often linked to biological activity produced by living organisms like microbes or larger creatures. When methane spikes were recorded on Mars, it sparked an exciting debate about the possibility of life on the red planet. What makes this discovery so intriguing is how methane behaves, as it doesn't last long in an atmosphere like Mars's because sunlight and chemical reactions break it down relatively quickly, meaning if it's being detected, something must be actively producing it. Scientists believe there are 2 possibilities. It could be a geological process like serpentinization, where certain types of rocks interact with water and heat to release methane. Or it could be biological, hinting at microbial life living beneath the surface. What's fascinating is how both explanations are equally plausible, given that Mars has evidence of underground reservoirs where water might still exist in liquid form, providing perfect conditions for methane-producing microbes to survive. On Earth, similar microbes thrive in extreme conditions, like deep underground or at the bottom of the ocean, without needing sunlight, suggesting that if similar life exists on Mars, it might be tucked away in subsurface environments, safe from the planet's harsh surface conditions. The European Space Agency's Trace Gas Orbiter and NASA's Perseverance rover are actively investigating these methane spikes, trying to trace their origin. The hope is that further data will reveal whether Mars's methane has a geological or biological source. If methane is linked to life, it could mean Mars isn't just a relic of the past, it could be harboring life even now. And even if it's geological, it tells us Mars is more dynamic than we ever imagined, with the answers out there and every new clue bringing us closer to unraveling the story. Water beneath the surface. Mars has always fascinated us, especially regarding water, as evidence suggests liquid water might still exist beneath its barren surface. This discovery could be a game-changer, not just for understanding Mars's history, but for the possibility of current life, as subsurface water reservoirs could hold the key to the planet's greatest secrets. In 2018, researchers using data from ESA's Mars Express orbiter detected a massive lake of liquid water buried beneath the South Polar ice cap, stretching about 12 miles across. The water is incredibly salty due to minerals that lower its freezing point, allowing it to stay liquid despite freezing temperatures, an environment similar to Earth's hypersaline lakes that support microbial life. The search hasn't stopped there, with radar signals suggesting additional water pockets near the original discovery. These findings suggest underground aquifers might spread across Mars, with some being relics from its wetter past, while others might be sustained by geothermal heat. What makes this thrilling is the potential for these reservoirs to support life, as even in Earth's harshest places, like Antarctica or the Dead Sea, microbial life thrives in salty, isolated waters. Mars might have similar conditions underground, where life could exist safely away from radiation. Future missions like ESA's ExoMars or NASA's Perseverance rover aim to investigate further. Each discovery brings us closer to understanding whether Mars is not just a world of ancient mysteries, but a planet harboring current life beneath its surface. Beneath its dusty exterior, Mars might hide the greatest scientific discovery, active water and possibly life itself. The red planet continues to surprise us, suggesting its most fascinating secrets lie not on its surface but deep within. Martian meteorites, seeds of life. Martian meteorites hold fascinating clues about life on Mars, as these pieces of the red planet, ejected by massive asteroid impacts, eventually made their way to Earth and contain hints suggesting Mars may have once hosted life. These cosmic messengers offer a unique glimpse into Mars's ancient past, with dozens found scattered across our planet. One famous example is ALH 84001, discovered in Antarctica in 1984, containing tiny structures that some scientists believe resemble fossilized microbial life, along with organic compounds and magnetite crystals that sparked intense debate about their origin. While the question of whether these features are biological remains unresolved, ALH 84001 transformed our perspective on Mars and life in the cosmos. What's even more intriguing is that these meteorites often contain organic molecules and amino acids, the building blocks of life, suggesting Mars may have had conditions suitable for life to emerge. Scientists are particularly fascinated by isotopic ratios within the meteorites, which indicate water interaction and chemical reactions that could support life, aligning with other evidence of ancient water on Mars. The implications extend beyond the meteorites themselves, as some researchers propose that Earth and Mars may have exchanged biological material through meteorite impacts in the distant past. If microbial life existed on Mars, these meteorites might have acted as seeds, spreading organisms between planets. This interconnection of our solar system raises profound questions about life's origins and distribution. Each meteorite analysis provides new insights into Mars's potential for harboring life. As we continue studying these cosmic travelers, they may reveal not only Mars's secrets but also clues about life's origins in the universe. These space rocks serve as bridges between worlds, connecting Earth's present to Mars's mysterious past. The panspermia hypothesis, Mars as a life seed. The panspermia hypothesis suggests that life might not have originated on Earth but was seeded here by microbial life traveling through space, with Mars often taking center stage as scientists speculate that Earth's life might have come from Martian meteorites. This idea fundamentally challenges our understanding of life's origins and suggests Earth and Mars share a deeper connection than previously thought. Mars stands as a strong candidate for being a life-seeding planet because billions of years ago, it may have been much more Earth-like, with flowing water, a thicker atmosphere, and life-supporting temperatures. During that early period when meteorite impacts were frequent in the solar system, powerful asteroid strikes on Mars could have ejected rocks containing microbial life into space, potentially reaching Earth over thousands or millions of years. The discovery of Martian meteorites on Earth proves such material transfer is possible, lending credibility to the theory. What makes this hypothesis particularly compelling is the remarkable resilience of certain microorganisms, as some bacteria and archaea can survive extreme conditions from freezing temperatures to the vacuum of space. If microbes could endure interplanetary travel, it suggests life might spread throughout the cosmos rather than arising independently in isolated locations. Mars might have acted as a starter planet, where early microbial life developed before being transported to Earth through cosmic debris. The implications of panspermia push us to reconsider life's boundaries and origins, suggesting that Earth's earliest organisms might have been part of a larger interplanetary system. This raises intriguing possibilities about life existing elsewhere in our solar system, potentially seeded from Mars or Earth. The panspermia hypothesis reframes life's story as a cosmic narrative that spans multiple worlds. These connections between planets suggest that understanding life's origins requires us to look beyond Earth and consider the complex interactions between celestial bodies over billions of years. Subsurface life in hydrothermal systems. Mars holds many mysteries, but one of the most exciting is the possibility of life beneath its surface, particularly in ancient hydrothermal systems where planetary heat interacts with water, environments that teem with extremophile organisms on Earth. Billions of years ago, Mars was radically different, with liquid water, volcanic activity, and a thick atmosphere that would have naturally created hydrothermal systems. When water seeped below the surface, it could have interacted with magma or other heat sources, creating perfect conditions for microbial life to emerge and potentially persist for millions or billions of years after the surface became inhospitable. Just as Earth's extremophiles thrive in hydrothermal vents and subglacial hot springs by living off chemical energy rather than sunlight, Martian life could have adapted to survive underground, feeding on minerals and compounds produced by hydrothermal activity. The discovery of methane and other gases on Mars hints at the possibility of ongoing microbial life in these subsurface environments, protected from the harsh surface conditions. Both NASA's Perseverance rover and ESA's ExoMars mission are investigating these possibilities, analyzing Martian rocks and soil for evidence of hydrothermal activity and potential biosignatures. Understanding Mars's hydrothermal history is crucial because these systems could have provided long-term habitable environments even as the planet's surface changed dramatically. If we find evidence of past or present life in these environments, it would revolutionize our understanding of habitability in the universe. The search for life in Mars's hydrothermal systems represents a convergence of geology, chemistry, and biology. These underground environments might have preserved conditions suitable for life long after Mars's surface became inhospitable. The study of Martian hydrothermal systems could reveal not just the planet's history, but also provide insights into how life might persist in extreme environments throughout the cosmos. Ancient oceans and Mars's lost atmosphere. Mars was once a world of water, where vast oceans covered parts of the planet's surface, as evidenced by dried-up river valleys, ancient shorelines, and water-formed minerals discovered by orbiters and rovers. These findings reveal Mars had a warmer, wetter climate capable of supporting large bodies of liquid water, making these ancient oceans prime candidates for the potential origin of Martian life. While some of Mars's water remains locked in polar ice caps or hidden underground, a significant amount has vanished into space, tied to the planet's atmospheric history. Long ago, Mars had a much thicker atmosphere rich in carbon dioxide, creating a greenhouse effect that trapped heat and allowed water to exist in liquid form. The loss of this atmosphere is believed to be caused by Mars's weak magnetic field, as unlike Earth, Mars lacks global magnetic shielding from the sun's powerful solar wind. Over billions of years, this solar wind stripped away the Martian atmosphere, leaving it thin and unable to retain heat, causing the planet's surface water to either freeze or evaporate into space. NASA's MAVEN spacecraft continues studying this atmospheric loss process, helping scientists reconstruct ancient Mars and assess whether its oceans could have supported microbial life. The existence of an ocean as vast as Earth's Arctic Ocean makes the possibility of past Martian life more compelling. Understanding the relationship between Mars's lost atmosphere and ancient oceans provides crucial insights into planetary evolution and habitability. Scientists are particularly intrigued by evidence suggesting these oceans persisted for hundreds of millions of years. The transformation from a water-rich world to today's desert planet serves as a stark reminder of how planetary conditions can change dramatically over time. Mars's ancient oceans tell a story of a planet that might have once been remarkably similar to early Earth, raising intriguing questions about life beyond our planet. And that wraps up our deep dive into 7 theories about life on Mars that could very well be true. Whether it's hidden microbes, ancient oceans, or Martian meteorites, the red planet continues to hold some of the universe's greatest secrets. If you enjoyed this cosmic exploration, be sure to like, share, and subscribe to InnoVision Tech. Don't forget to hit the bell icon to stay updated with our latest videos. Until next time, keep reaching for the stars with us. Have you ever wondered what secrets lie beyond the Milky Way in the smaller galaxies that orbit it? These satellite galaxies are not just cosmic companions. They hold unique mysteries and fascinating insights into the universe's history and evolution. Did you know that some of these galaxies are newcomers, while others have been around for billions of years? Join us as we explore the 7 most intriguing properties of the Milky Way's satellite galaxies and uncover the hidden wonders of our cosmic neighborhood. The diversity of satellite galaxies. The Milky Way's satellite galaxies are a marvel of variety, each one with its own story to tell. Some, like the large and small Magellanic Clouds, are bold and bright, easy to spot even with the naked eye from certain parts of Earth. Others, such as the ultra-faint dwarfs, are barely detectable, their faint glow hiding some of the universe's most ancient secrets. This range in brightness, size, and structure is what makes these galaxies such an incredible subject of study. In some of these satellites, you'll find regions teeming with young, newly formed stars. For instance, the Large Magellanic Cloud is rich with star-forming nebulae, where hot, massive stars shine brightly against swirling clouds of gas and dust. On the other hand, galaxies like the Sculptor or Bootes dwarfs are much quieter. These galaxies contain predominantly older stars, remnants from an era not long after the Big Bang, making them cosmic time capsules that offer a glimpse into the past. The way these satellite galaxies interact with the Milky Way is equally fascinating. Some, like the Sagittarius Dwarf Galaxy, are in the process of being consumed by our galaxy's gravity, leaving streams of stars in their wake as they are slowly pulled apart. Others, like the Magellanic Clouds, maintain a more stable orbit, though even they are subtly influenced by the gravitational forces of the Milky Way. These interactions not only shape the satellites but also contribute to the formation and evolution of the Milky Way itself. This diversity is more than just interesting, it's crucial for understanding the broader picture of galaxy formation and evolution. Each satellite galaxy is like a piece of a cosmic puzzle, revealing how galaxies merge, interact, and grow over billions of years. By studying their unique characteristics and behaviors, scientists can piece together the history of the universe, gaining insight into the forces that shape our galaxy and the cosmos beyond. Galactic cannibalism, the Milky Way's appetite. The Milky Way isn't just a majestic spiral galaxy, it's also a cosmic predator with a history of consuming smaller galaxies. This process, called galactic cannibalism, is how our galaxy grows and evolves over time. When smaller galaxies stray too close, the Milky Way's powerful gravity begins to pull them apart, gradually assimilating their stars, gas, and dark matter into its own structure. It might sound destructive, but this process is a key driver of galaxy formation and evolution. One of the most famous examples of this is the Sagittarius Dwarf Galaxy, which is currently being devoured by the Milky Way. Streams of stars from this galaxy, known as tidal tails, are now stretched out across the sky, forming a bridge of stellar material that wraps around our galaxy. These stars, originally part of the dwarf galaxy, are becoming part of the Milky Way's outer halo, blending seamlessly into its massive structure. But Sagittarius isn't the only galaxy to face this fate. Scientists have discovered that the Milky Way has absorbed numerous dwarf galaxies over billions of years. Some of these mergers happened so long ago that the evidence has been completely incorporated into the Milky Way, while others, like the Gaia-Enceladus merger, have left behind distinct populations of stars with unique compositions and motions. Each act of galactic cannibalism leaves subtle traces that astronomers can study to uncover the Milky Way's growth history. This process isn't unique to the Milky Way, it's a natural part of how galaxies evolve in the universe. As galaxies collide and merge, they create stunning displays of cosmic interaction, from starbursts to streams of gas and dark matter. For the Milky Way, this appetite for smaller galaxies has been essential to its development, helping it grow into the massive, dynamic structure we see today. By studying galactic cannibalism, we learn not only about the Milky Way's past but also about the dynamic forces shaping galaxies across the cosmos. Star formation and tidal interactions. The relationship between the Milky Way and its satellite galaxies isn't just a one-sided gravitational pull. It's a dynamic interaction that can spark some spectacular events. When the gravity of the Milky Way tugs on a smaller satellite galaxy, it creates tidal forces that can compress gas and dust within the satellite. This compression can ignite bursts of star formation, leading to new generations of stars lighting up the galaxy. It's like a cosmic trigger for stellar creation. A great example of this is the Large Magellanic Cloud, one of the Milky Way's most prominent satellite galaxies. Its close gravitational interaction with the Small Magellanic Cloud in the Milky Way has stirred up its internal gas, creating regions like the Tarantula Nebula. This nebula is a star-forming powerhouse, producing some of the most massive and luminous stars in the universe. These tidal interactions are responsible for transforming otherwise quiet galaxies into vibrant star-filled regions. The effects of tidal interactions aren't limited to the satellite galaxies themselves. The Milky Way also feels the impact as streams of gas and stars pulled from the smaller galaxies feed its outer regions. This influx of material can fuel star formation in the Milky Way, especially in its outer halo. These tidal streams act as bridges, connecting the satellite galaxies to their massive host while enriching both with fresh material for future generations of stars. These gravitational dances are more than just beautiful. They provide essential insights into how galaxies evolve and sustain themselves over billions of years. They show that even smaller galaxies play a significant role in shaping the larger cosmic structures around them. By studying these interactions, astronomers uncover the delicate balance of forces that drive star formation and maintain the dynamic nature of galaxies, like the Milky Way. The role of dark matter in satellite galaxies. Dark matter is one of the most mysterious and fundamental components of the universe, and it plays a crucial role in the existence and behavior of the Milky Way's satellite galaxies. These small galaxies are often surrounded by an invisible halo of dark matter that provides the gravitational glue holding them together. Without it, these galaxies, composed of relatively few stars and sparse gas, wouldn't have the gravitational strength to resist being torn apart by the Milky Way's immense pull. For example, studies of the Fornax and Sculptor dwarf galaxies reveal that their motions and structures only make sense when the presence of dark matter is factored in. By measuring the velocities of stars within these galaxies, astronomers have concluded that there's far more mass present than can be accounted for by visible matter alone. This unseen mass, dark matter, dominates their gravitational dynamics, acting as the unseen architect shaping their formation and survival. The influence of dark matter extends beyond holding satellite galaxies together. It also dictates how these smaller galaxies orbit the Milky Way. The vast dark matter halo enveloping our galaxy creates a kind of gravitational scaffolding that guides and stabilizes the orbits of satellite galaxies. This interaction between the Milky Way's dark matter halo and that of its satellites determines how they cluster, move, and even collide. These interactions give astronomers vital clues about the larger dark matter structure of our galaxy and the universe as a whole. Understanding the role of dark matter in satellite galaxies isn't just about solving cosmic puzzles. It's a way to test our models of the universe. By comparing the observed behaviors of these galaxies with simulations, researchers can refine their understanding of dark matter itself. The study of these small dim companions is unlocking profound insights into the nature of a substance that remains one of the greatest enigmas in modern astrophysics. It's a reminder that even the unseen has a massive impact on shaping the cosmos. Newly discovered satellite galaxies. The Milky Way's family of satellite galaxies is growing, thanks to advanced telescopes and innovative research methods. Over the last few years, astronomers have uncovered a surprising number of new satellite galaxies orbiting our own. These discoveries not only expand our galactic map, but also offer a wealth of insights into the dynamics of galaxy formation and evolution. Some of these newly found galaxies are so faint and compact that they were nearly invisible until now. One example is the discovery of ultra-faint dwarf galaxies, which are among the smallest and dimmest galaxies known. They contain just a handful of stars spread out across vast distances, making them difficult to detect. However, instruments like the Dark Energy Camera and data from the Gaia mission have made it possible to spot these elusive objects. These faint galaxies, are not only fascinating in their own right, but also help scientists explore the limits of galaxy formation in the universe. Some of the new satellite galaxies have peculiar orbits or unusual properties that set them apart from others. For instance, the Antlia 2 galaxy, discovered in 2019, is enormous in size yet incredibly faint. So faint that it was dubbed the ghost of the Milky Way. Its discovery raised intriguing questions about how galaxies can form and survive in such extreme conditions. Each new find, whether it's a faint dwarf or a massive but hidden structure, challenges what we thought we knew about the cosmos. These discoveries are more than just cataloging new objects. They give astronomers a closer look at the Milky Way's past interactions and provide essential data for understanding the role of dark matter, the formation of galactic halos, and the impact of gravitational forces on galaxy survival. The ongoing search for new satellite galaxies is like assembling a cosmic puzzle, where each new discovery adds a piece to the grand picture of how the Milky Way and its companions came to be. The unique histories of satellite galaxies. Satellite galaxies orbiting the Milky Way are not just passive companions, they carry unique stories of their origins and transformations. Each satellite galaxy has a history shaped by countless interactions with larger galaxies, the pull of gravity, and the dynamics of their own stars and dark matter. These smaller galaxies, despite their size, can reveal astonishing details about the evolution of the cosmos and the Milky Way itself. Some satellite galaxies were once thriving and independent systems before being captured by the Milky Way's gravity. Over billions of years, their orbits have often brought them dangerously close to our galaxy, stripping them of stars, gas, and dark matter. This gravitational interaction, called tidal stripping, has left some of them almost entirely bare, reduced to sparse collections of stars barely clinging together. These remnants are like ancient ruins, offering clues about the destructive power of galactic interactions. A fascinating part of their histories involves the stars they carry. Many satellite galaxies show evidence of multiple generations of star formation, with some containing stars that are among the oldest in the universe. By studying these ancient stars, astronomers can piece together events that occurred shortly after the Big Bang. Some of these galaxies, like the Sagittarius dwarf galaxy, even show traces of having merged with other smaller systems before becoming satellites of the Milky Way. These interactions create a tapestry of histories that reflect the chaotic processes of galaxy formation. What makes these histories even more compelling is the role of external influences. Some satellite galaxies have experienced bursts of star formation triggered by interactions with the Milky Way's halo, while others have had their growth stunted by the lack of gas due to environmental factors. Each satellite galaxy represents a different chapter in the story of cosmic evolution, giving us a window into the processes that have shaped galaxies across the universe. Their unique paths remind us that even in the vastness of space, every object carries a story worth exploring. The future of the Milky Way's satellite galaxies. The Milky Way's satellite galaxies aren't static entities, they're part of a cosmic dance that continues to evolve. Over the coming billions of years, the gravitational interplay between these smaller galaxies and the Milky Way will shape their futures in ways we're only beginning to understand. Some will survive as companions, while others may be torn apart, merging their stars and materials with the larger galaxy. Many of these satellite galaxies are gradually spiraling inward due to the immense gravitational pull of the Milky Way. This process will eventually lead to their disruption and absorption, a phenomenon known as galactic cannibalism. As they approach the Milky Way's core, tidal forces will strip away their stars, gas, and even dark matter, scattering these materials throughout the larger galaxy. The Sagittarius dwarf galaxy is a perfect example of this, as its remnants are currently merging with the Milky Way, leaving a stellar stream in its wake. Other satellites may remain relatively intact, orbiting the Milky Way for billions of years to come. The Large and Small Magellanic Clouds, the most prominent of these satellite galaxies, are expected to collide with the Milky Way in the distant future. Their interaction is likely to trigger bursts of star formation, revitalizing regions of our galaxy and adding new stars to its already sprawling population. Such collisions will also help scientists refine models of galaxy evolution by providing real-time examples of these transformative events. As technology advances, future telescopes and space missions will provide clearer insights into these satellites' trajectories and ultimate fates. These discoveries won't just reveal the destinies of these smaller galaxies, but also offer clues about the long-term future of the Milky Way itself. The story of our galaxy is intricately tied to the lives of its satellites, and studying their futures helps us understand the larger picture of cosmic evolution. Their dynamic interactions remind us that the universe is far from a quiet place. It's a constantly changing, interconnected web of matter, energy, and motion. That concludes our cosmic journey through the Milky Way's satellite galaxies, from their fascinating diversity to their dynamic past and intriguing future. These tiny companions hold the keys to unlocking the mysteries of galaxy formation, evolution, and the nature of the universe itself. If you enjoyed this exploration, be sure to like, share, and subscribe to InnoVision Tech. Don't forget to hit the bell icon to stay updated with our latest videos. Until next time, keep exploring the wonders of the cosmos with us. Ever wondered what holds the universe together in a vast web of cosmic connectivity? Cosmic filaments, the universe's grand highways, stretch across billions of light-years, linking galaxies, stars, and dark matter in a delicate, almost invisible lattice. How do these structures form, and what secrets do they reveal about the universe's evolution? Join us as we unravel 10 fascinating facts about cosmic filaments and their pivotal role in the cosmic web. Cosmic filaments are the universe's largest structures. Cosmic filaments are not just large, they are the largest known structures in the universe, stretching for hundreds of millions of light-years. These colossal threads of matter weave a framework connecting galaxies, clusters, and superclusters in a massive web-like pattern. The filaments form part of the cosmic web, a term that describes the large-scale structure of the universe. Made primarily of dark matter, gas, and galaxies, these filaments are bound together by gravity. Their immense size and intricate design reveal the universe's organization on its largest scale. Through simulations and observations, scientists have mapped out these filaments, showing how they thread through vast voids of seemingly empty space. The filaments' intersections are hubs where galaxy clusters form, while their threads serve as highways along which galaxies and matter travel. What's truly fascinating is how these structures emerged from tiny density fluctuations after the Big Bang. Over billions of years, gravity sculpted these filaments, transforming the chaotic early universe into the interconnected masterpiece we observe today. Dark matter is the backbone of cosmic filaments. While visible galaxies may outline cosmic filaments, it's dark matter that forms their backbone. This mysterious substance, which makes up about 27% of the universe's mass energy content, is largely responsible for the gravitational pull that shapes and holds these structures together. Dark matter doesn't interact with light or normal matter directly, making it invisible and detectable only through its gravitational effects. Scientists have used advanced simulations and techniques like gravitational lensing to understand how dark matter forms the scaffolding of the cosmic web. As dark matter clumps together, it creates gravitational wells that attract ordinary matter, forming the galaxies and stars that we see within filaments. This interaction between dark matter and visible matter highlights the unseen forces that govern the cosmos. By studying cosmic filaments, researchers hope to unlock more about the elusive nature of dark matter. These massive structures serve as laboratories for testing theories and understanding how dark matter influences the universe's evolution on grand scales. Filaments act as cosmic highways for galaxies. Cosmic filaments don't just connect galaxies, they guide their movement. Galaxies travel along these vast structures, influenced by the gravitational pull of dark matter and the underlying filamentary network. This movement isn't random. It follows a pattern that scientists refer to as cosmic flow. Galaxies and matter stream along the filaments toward denser regions like clusters and superclusters. This flow creates a dynamic, ever-evolving cosmic web, where filaments serve as pathways for the redistribution of matter. The role of filaments extends beyond mere transportation. They also influence galaxy formation and evolution. As galaxies travel through these dense regions, they interact with the hot gas and other matter within the filaments, which can trigger star formation or even strip galaxies of their gas, affecting their development. Observations from telescopes like the Sloan Digital Sky Survey and simulations like the Millennium Simulation have provided detailed maps of these flows, showcasing the intricate ballet of matter along the filaments. These studies highlight the filament's importance in shaping the universe's structure and dynamics. Cosmic filaments contain vast reservoirs of gas. Beyond galaxies and dark matter, cosmic filaments hold enormous amounts of diffuse gas, often referred to as the intergalactic medium. This gas, primarily hydrogen, fills the spaces between galaxies and serves as the raw material for star and galaxy formation. Recent observations have shown that these gas reservoirs can be incredibly hot, reaching temperatures of millions of degrees. This hot gas emits X-rays, which astronomers use to study the filament's composition and distribution. Advanced telescopes like the Chandra X-ray Observatory have been instrumental in revealing the properties of this hidden gas. The gas within filaments also provides clues about the universe's chemical evolution. Elements like carbon, oxygen, and iron, produced by stars and supernovae, are dispersed into the filaments, enriching the intergalactic medium over time. These gaseous reservoirs play a vital role in the cosmic ecosystem, fueling galaxy growth and maintaining the balance of matter across the universe. By studying the gas and filaments, scientists gain insights into the processes that drive the universe's ongoing evolution. Filaments influence the growth of galaxy clusters. At the intersections of cosmic filaments lie galaxy clusters, some of the most massive structures in the universe. These clusters form where multiple filaments converge, creating regions of intense gravitational pull that attract vast amounts of matter. The role of filaments in cluster formation is profound. As matter flows along the filaments, it accumulates at these intersections, fueling the growth of clusters. This process, known as hierarchical clustering, is a cornerstone of modern cosmology, explaining how structures grow over time. Galaxy clusters within filaments are often connected by bridges of matter, visible as faint X-ray emissions or gravitational lensing patterns. These connections provide direct evidence of the cosmic web's interconnected nature and its role in shaping the universe. Understanding how filaments feed galaxy clusters helps scientists unravel the complex processes behind structure formation. Observations of clusters and their surrounding filaments also shed light on the behavior of dark matter and the distribution of energy in the cosmos. Filaments shape the universe's cosmic landscape. Cosmic filaments are more than just physical structures. They define the universe's large-scale geometry. Their intricate patterns of dense threads and empty voids create a tapestry that reflects the underlying physics of the cosmos. This cosmic landscape is a direct result of initial conditions set by the Big Bang. Tiny fluctuations in the density of matter expanded and grew under the influence of gravity, creating the web-like structure we see today. The study of these patterns provides critical information about the universe's origins and its subsequent evolution. The cosmic web also serves as a testing ground for theories about dark energy, the mysterious force driving the universe's accelerated expansion. By analyzing how filaments and voids evolve over time, scientists can probe the effects of dark energy on the universe's structure. Filaments are not static, they change and evolve, influenced by gravitational interactions, galaxy movements, and cosmic expansion. This dynamic nature adds to the richness of the cosmic web and underscores its role as a living, evolving system. Filaments are a bridge between galaxies and voids. Cosmic filaments don't just connect galaxies, they serve as a transition zone between the dense hubs of galaxy clusters and the vast empty expanses known as cosmic voids. These voids, which make up most of the universe's volume, are regions with few or no galaxies, and filaments act as the intricate threads bordering these immense regions of emptiness. The boundaries between filaments and voids are fascinating areas of study as they represent a stark contrast in the density of matter. Filaments are rich with galaxies, gas, and dark matter, while voids are relatively barren, containing only traces of matter. This contrast creates unique environments where scientists can study the forces shaping the universe. Galaxies near the edges of filaments experience gravitational influences that can affect their shape, speed, and evolution. As galaxies fall into filaments from voids, they often encounter streams of gas and dark matter that fuel star formation or alter their structure. These interactions highlight the dynamic relationship between dense filaments and the vast voids they surround. Exploring this bridge between galaxies and voids offers valuable insights into how matter is distributed and how different environments influence the evolution of cosmic structures. Filaments not only connect the universe but also define its boundaries, shaping the interplay between its densest and emptiest regions. The cosmic web illuminates the universe's early days. The study of cosmic filaments has become a powerful tool for understanding the universe's origins. These structures hold clues about the conditions of the early universe, particularly the moments following the Big Bang when the first density fluctuations began to take shape. Using advanced simulations and telescopes, scientists can trace the evolution of filaments back billions of years. The earliest filaments formed when tiny density variations in the primordial universe grew under the influence of gravity. These early threads laid the foundation for the massive cosmic web we see today. The distribution and alignment of filaments also provide information about the physics of the early universe. For example, studying how filaments are oriented and how galaxies are distributed within them can reveal the effects of cosmic inflation, the rapid expansion that occurred just after the Big Bang. By observing ancient light, such as the cosmic microwave background, and mapping the positions of galaxies and filaments, researchers piece together a timeline of cosmic evolution. The story of filaments is not just about the present-day universe, but also about the profound forces that shaped it from the very beginning. Filaments may harbor missing baryonic matter. For years, scientists have been searching for the universe's missing baryonic matter, the ordinary matter composed of protons, neutrons, and electrons that make up stars, planets, and people. Observations suggest that much of this baryonic matter is unaccounted for, and cosmic filaments may hold the answer. Research indicates that this missing matter resides in the hot, diffuse gas within filaments, known as the warm-hot intergalactic medium. This gas, spread out across the vast stretches of the cosmic web, is difficult to detect directly but emits faint X-rays and ultraviolet light that specialized telescopes can observe. Studies using telescopes like the Chandra X-ray Observatory and the Hubble Space Telescope have confirmed the presence of this gas, providing a clearer picture of where the universe's baryonic matter is hiding. This discovery helps resolve one of cosmology's biggest mysteries and underscores the significance of filaments as reservoirs of cosmic material. Understanding the distribution of baryonic matter in filaments also sheds light on galaxy formation, star birth, and the dynamics of the intergalactic medium. Filaments are not just highways for galaxies, but also storehouses of the universe's fundamental building blocks. Cosmic filaments are a glimpse into the universe's future. The cosmic web, with its sprawling filaments and dense clusters, is constantly evolving. Over billions of years, gravitational forces continue to pull matter along filaments toward the densest regions, causing clusters and superclusters to grow even larger. This gradual process offers a glimpse into the universe's future. As filaments funnel matter into these hubs, the surrounding regions become emptier, creating more pronounced voids. The cosmic web structure becomes increasingly defined, with sharper contrast between dense